Okay, in this video, we're going to determine whether or not a function is even or odd. So a function is even if we take the input values and we see what we get, and then we take the opposite of those input values. If we get the exact same results as before, then the function is even. So that's what this f of negative x equals f of x is. It means that if we evaluate the function at points that we choose, and then we get those outputs, if we take the opposite of those points that we chose and plug it in and get the same outputs as before, then our function is even. So, in other words, negative input values are going to give you the same outputs or same results as their positive opposites will. So, visually, even functions are symmetric with respect to the y-axis. In other words, if we graph it and print it out, we can fold the graph over the y-axis, and the left and right halves will lie on top of each other perfectly. They'll align perfectly. A function is odd if f of negative x equals negative f of x. So again, if we look at some input values and then take their opposites, if the output values become opposites, then a function is odd. So negative input values are going to give you the opposite outputs as their positive opposites, which sounds kind of weird when you say it that way. Odd functions are symmetrical with respect to the origin. In other words, you could print it out, fold it once along the y-axis, and then a second time fold it over the x-axis. So fold it over the y, and then take that folded piece of paper and fold it over the x-axis, and you'll get the graph to align on perfectly with itself. So even gives you equal outputs, odds give you opposite outputs, and let's take a look at example 3. So we're going to determine whether or not each of the following functions is even, odd, or neither. So we have f of x is 5 over 2 minus x squared. So let's take a look at the graph of that. So here we have f of x is 5 over 2 minus x squared. It seems to be symmetric with respect to the y-axis. It looks like the left half of the graph is a mirror image of the right half of the graph. As far as determining whether or not it is, if we replace f of x with f of negative x, we'll get 5 over 2 minus, in parentheses, negative x squared. When we square negative x, we get just x squared. So when we evaluated f of negative x, we get the exact same answer as we did before, as what we started with. So this is an even function. So we got the same output values when we replace x with negative x. Numerically, if we look at an example like f of 5, that gives us this goofy looking decimal here. If we evaluate f of negative 5, we get the exact same goofy decimal, and that'll be true for any value of x that we plug in. We'll get the exact same output if we change it from 5 to negative 5 or negative 5 to 5. Just take their opposites, nothing's going to change. All right, example B, we have g of x equals 5x over 2 minus x squared. So now we put an x in the numerator. Let's see what happens there. So let's get a visualization of this first. And it definitely doesn't appear that the left half of the y-axis is the same as the right half. But maybe if we flip it over the y and then flip it over the x, or vice versa, that would be an example of an odd function. So let's replace x with negative x. So 5 times negative x over 2 minus, in parentheses, negative x squared. It gives us negative 5x over 2 minus x squared, which, if we pull this negative out of the numerator, we have negative 5x over 2 minus x squared. Well, that's the exact same thing we started with. So that's negative of what we started with. These are opposite outputs. This is an odd function. So if we flip this over the y-axis and then flip that once more over the x-axis, this graph will align with itself. To put it in terms of numbers, which for me is a lot easier. So if we look at g of 7, we get this goofy decimal here. If we look at g of negative 7, take the opposite of 7, notice the only thing that changed from our outputs was the sign. So we went from negative to positive. So if the sign is the only thing that changes, then we have ourselves an odd function. All right, part C, 5x over 2 minus x cubed. So we're just kind of really tweaking these a little bit. Let's take a look at that graph. So here's 5x over 2 minus x cubed. It doesn't look like the left and right halves are equal, and it doesn't look like if I flip it over the y and then flip it over the x that I'll get the graph to line on itself. I have a suspicion this is neither, so let's take a look. If we replace x with negative x, we get negative 5x up top. Negative x cubed is negative x cubed, so negative x times negative x times negative x is negative x cubed, and we have minus a negative of x cubed is plus x cubed. So if we pull that negative out, we do not get the exact same thing that we started with. We have a plus in this denominator, we have a minus in this one. So this one's neither odd nor even. And we can actually see that from a numerical perspective. It's nice when it's neither, because all it takes is one counterexample. So if we look at something like h of 4, also don't forget we have variables in denominators, so watch that domain. We get this goofy looking output number. If we do h of negative 4, we're not even close to the same number or even just the opposite. So this one is definitely neither odd nor even. All right, just a couple more. Part D, I of x is 5x over 2x minus x cubed. So if we take a look at that graph, here's I of x. It appears to be symmetric with respect to the y-axis. So I have my suspicions this is an even function. Let's confirm. If we replace x with negative x, we get 5 times negative x over 2 times negative x minus negative x cubed. That's negative 5x on top, negative 2x here, and just like we saw in the last example, we'll have plus x cubed. We can factor a negative 1 out of this denominator and give us negative 1 times 2x minus x cubed, and then negative 5x divided by negative 1 is positive 5x. So we end up with the exact same thing we had at the beginning. This is an even function. I of x is an even function. And we can see that with some inputs to confirm that. Let's go I of 7. We get that decimal. If we do I of negative 7, we get the exact same decimal. So any input we give, its opposite, assuming it's in the domain, its opposite will give us the exact same output. So if the outputs are equal, it's even. Even, equal, opposite, odd. All right, finally, as you saw from my my little quick to progress to the next slide here, j of x is x squared minus x over 100 minus 1. So let's take a look at that one. So here's the graph, and it appears to be symmetric with respect to the y-axis. So suspicions on the graph would say this is an even function, but let's see. If we replace x with negative x, here, negative x in parentheses squared, negative x times negative x, it's going to give us positive x squared. Negative x over 100 is positive x over 100, and then minus 1. And this expression is not the opposite of this expression, nor is it equal to it. This one's neither odd nor even. And this is a good example because if you look at just the graph alone would suggest that it's an even function. But if we pick a number such as, let's say, j of 5, we get 23.95. If we do j of negative 5, we don't get the same thing, and we don't get the opposite. Excuse me. So this is neither odd nor even. So be careful with just the graphs. All right, that about does it for this video. I'll see you in the next one.